Hi everyone, thanks for coming to this virtual lab tour. Today we're going to show you the atom laser experiment here at the University of Amsterdam. So here is our atomic oven. Here we heat the strontium atoms to produce the hot vapor. The atoms travel through the Siemens lower axis.
All right. Good morning. My name is Hossein Sadeghpour. I'm about 8,000 miles away from you, sort of as an absentee organizer, with apologies that I could not be there. But I was promised that later, maybe in the year, I could come. But without further ado, let me start the second day. And the first speaker is Florian Schreck from Van der Waals Zeeman Institute at the University of Amsterdam. And I understand he will talk about the continuous BEC of strontium atoms. So without further ado, Florian, please.
Thank you. So, everything fine? Okay. So thank you very much for being here. And thanks a lot to the organizers for inviting me to this nice conference in this very interesting place. It's my first time in India, so I'm enjoying it a lot. So I'm going to speak about continuous Bose-Einstein condensation and optical clocks. This is research in the field of sensing, and sensors are really everywhere. Now, okay. Oh, it did work. It was just very slow. Okay. Now, sensors are really everywhere. This little cute jumping spider uses it to find its prey and to find food. And what I find funny is that there's a sort of convergent evolution happening between biology and something's not working here. So there's always a delay of several seconds till the new slide comes up. And technology, as you can see here. Now, our phones are chock full with sensors, which allow them to tell you where they are and so on. But these are all classical sensors. Here we are, of course, interested in building ultra-cold atom quantum sensors, such as optical clocks or atom interferometers. And with those sensors, you can do very interesting things. Anna Maria, you have already talked about optical clocks a lot and told us that they are great for tests of fundamental physics. Does the electron to proton mass ratio change, for example, the synchronization of radio telescopes, detection of gravitational waves, maybe one day, and of course, the study of many-body physics. But clocks also have societal applications. These really exquisite optical clocks can be used for geodesy at the centimeter level. And less good optical clocks already can be used for telecom network synchronization, terrestrial navigation, underground exploration, and so forth. Okay, so we want to improve clocks, and to see how, I will first walk you through the operating scheme of a normal clock. So we typically use strontium, and there we start by laser cooling on a very broad line width transition, 30 megahertz wide, a blue transition, with which we can scatter millions of photons per second, and that's really needed to slow the atoms, the fast atoms coming out of an oven. But on this broad transition, we cannot cool very much, only down to 1 millikelvin because of the Doppler limit. But in strontium, we also have a narrow transition. We can switch over to that one. It's a 7 kilohertz line width transition. This allows us to cool to microkelvins within a few hundred milliseconds. Now the atoms are cold enough to be loaded into a magic wavelength optical lattice, and we can perform spectroscopy. Right. And when we read out the state of the atoms by fluorescence, we heat up the sample, and typically it's lost. So for the next spectroscopy run, we need to prepare yet another atomic ensemble, and that takes some time. Now, lasers are nasty. They drift away in frequency if you don't do something to them. So people built very exquisite, ultra-stable optical resonators onto which the laser is locked on the short term. Right here, Anna Maria, you showed already some pictures about that. Okay. So the optical resonator gives us the stability of the laser on the time scale of a few 10 seconds or so, and the atoms give us the absolute accuracy and the long-term stability. And that's it. That's your optical clock. It can have, nowadays there are many clocks which have a precision of 10 to the minus 18. That would be 1 second off over the lifetime of the universe. But these clocks, they tick at a frequency of 460 terahertz. Not everybody likes their clock to tick that fast. People who don't like this, they just purchase an optical frequency comp, which can be used to translate this high optical frequency into any other laser frequency or radio frequency that you would like. Okay, so what can we do to improve clocks? So you saw that we create atomic ensembles every once a second or so to perform spectroscopy. This is, of course, inelegant. It would be much nicer if we could have atoms available all the time in order to phase lock our laser onto the atomic transition continuously. And this is one of our big goals. If you could do this, if you could lock the laser all the time to the atoms, you could even get away with an optical resonator that's not as crazily complicated as the ones that Anna Maria showed you. And that would be good if you want to operate your clock on a moving vehicle where you have a bit of shaking. Okay, so now why would it be so great if you could have a quantum sensor that measures continuously? Let me explain this to you with the example of an atom interferometer that's used as a gyroscope to measure the position of a boat in the waves. You see, you're on a boat and it's in the ocean and there's strong waves and the boat is shaking. Now, with this pulsed measurement scheme, it can easily happen that you prepare your atoms while the boat is in this position. And then prepare, measure, prepare, measure. Yeah, and then you will think the average, your average measurement results will show your boat in this orientation, and you will navigate like that and arrive at the completely wrong destination, because really the real average was, of course, boat being horizontal. And this error is called the error from the Dick effect, and it influences all pulsed measurement devices. We want to get rid of it by continuous measurement. So if you want to build a continuous ultra-cold atom quantum sensor, we need a good continuous source of ultra-cold atoms with high flux and high density. If you push these requirements, low temperature, high density, to its limit, you arrive, of course, at Bose-Einstein condensation. And in this case, it's a continuous stream of atoms, so it's a continuous atom laser. So we put ourselves the goal to build just that. And here's the outline of my talk. So I will describe you our way towards a continuous wave atom laser. I'll show you how we create continuously Bose-Einstein condensates. And to keep these Bose-Einstein condensates alive, we created a microkelvin called strontium beam in the dark, which is also great to build clocks. And at the end, I'll briefly show you other experiments we have in our lab. Let's start with creating a laser beam. So in optics, you know how to do it. You just take an optical cavity, fill one mode of the cavity with lots of photons, make one mirror a little bit transparent, and out comes a laser beam. With ultra-cold atoms, people have done this exactly in the same way. You laser cool an evaporatively cooler gas, create a BEC in a trap, and then you punch a hole into your trap and out-triple atoms by gravity. That's your atom laser beam. Now, these laser beams don't last very long because after a short while, all the photons or atoms are just gone. But in optics, we know exactly what to do. We just put an inverted gain medium into our cavity, which by stimulated emission puts more photons into the mode. And you can do the same thing with atoms. You just put a thermal gas of atoms around your BEC, and that thermal gas, if it has a very high phase-space density, it will drive more atoms by Bose-enhanced elastic collisions into the BEC mode. Now it lasers longer, but not indefinitely so. To do so, we need to keep the inversion of our gain medium. So we pump it somehow. And in the case of atoms, it means we just fill new atoms into this region around the BEC, and to keep this thermal gas at high phase-space density, we just use laser cooling. Right? And like this, we can overcome the losses that we have. By the way, in the case of a BEC, the losses are dominated, at least in our system, by three-body recombination, right? Molecule formation. It's like a chemical fire which burns away our atoms, and we overcome this by continuous pumping. Now, we didn't yet completely reach a moving atom laser beam, but we implemented all of this here and created continuous Bose-Einstein condensation. So essentially, we have the same system as an optical laser, but with in-transparent cavity mirrors. Good. Now let's take a look at the history of atom lasers. Pulsed atom lasers were done a very long time ago, over 25 years ago, just in the way I showed. And here are images of these atom laser beams falling downwards. And they last typically at decent high flux for 100 milliseconds or so. And then you need to create a new BEC, which can take several seconds. So this is not a good duty cycle for applications. And people have worked very strongly to push this further. Early on, Catalyst Group, for example, showed that they could replenish a BEC over and over so that they have a BEC existing at all times. David Guéry-Audelin and Jean Dalibard showed continuous evaporative cooling. Jean-Claude's nice optical pumping mechanism, Tilman Pfau and Alex Griesmeier, continuous trap loading. But yeah, especially the last three experiments, they suffered because they used alkalis or chromium, and those elements cannot be laser cooled very well. In addition, the Bose-Einstein condensate really is incompatible with laser cooling, because if you have a BEC, the atom stands still, and if there's a stray laser cooling photon arriving, as absorbed by your BEC atom, the BEC atom gets a kick and becomes a thermal atom, and so the BEC is destroyed. Now we are working with strontium, and this element offers new possibilities. We have this broad and narrow laser cooling transitions, and you also have a trick to render atoms transparent against laser cooling light. And when we are still back in Innsbruck, we made a precursor experiment demonstrating that we can hold a BEC inside a laser-cooled thermal cloud. So the core, the central part of my atom laser scheme. How did we do this? So this was completely a pulsed experiment. We first load a lot of atoms laser cooled on the blue transition, which is necessary because the atoms are really fast when they come out of the oven. Then we switch to the red laser cooling transition and make a magneto-optical trap with 1 microkelvin temperature. Now this mod has to work hard. It also has to levitate the atoms against gravity, which is really not easy for such a narrow intercombination line mod. So you need to crank up the laser power a lot. And that means you have a lot of multiple scattering and photo association, and the density in such a mod doesn't go very high. But if you now levitate your gas cloud in an optical dipole trap, you are free to reduce the laser cooling intensity a lot, reduce the multiple scattering, and then you can reach a phase-space density of already 0.1. And after Bose-Einstein, we just need to reach 2.6. So how do we do this? We just add a little dimple dipole trap to the reservoir trap in which we hold most of our gas. And just like air at ocean level is denser than air on Mount Everest, the gas in the middle of the dimple will be denser. But it will be at the same temperature because we have plenty of elastic collisions thermalizing the gas in the dimple with the outside laser-cooled reservoir. Now we just have to overcome the light scattering problem, and we render the atoms inside the dimple transparent by light shifting the optically excited state vastly out of resonance. With yet another laser beam targeted at this region. Here you see absorption images taken on the narrow intercombination line. It's transparent here in the middle. Yeah? There are as many atoms as in the middle image, but they're just not showing up. Exactly what we want. And if we now look, we just shoot away the atoms in the reservoir, make a time of flight absorption image. You can see here a nice thermal cloud surrounding a BEC. The BEC shows up elliptically because in the trap it has mean field energy that's released on expansion in the strongly confined direction, which here is vertical. Okay, So if you see any elliptical things on such pictures in my talk, it's probably a BEC. Now, this is not a continuous experiment. It was all pulsed. So to go to a continuous atom laser, okay, we need to outcouple, but we also need to put new atoms into our thermal gas, yeah, because it burns away by three-body recombination very quickly. And that can't be done with a traditional machine because of the problem that we need to use this broad blue laser cooling transition to capture the atoms from the oven, but we can't protect our BEC from these photons. The light shifting trick wouldn't work. So we built a new machine in Amsterdam. Here you see strontium oven, blue Siemens law, and then we have a 2D blue mod sending atoms downwards into a second vacuum chamber where we allow ourselves to use only the red laser cooling light. And down here we have a vertical Siemens law, slowing the falling atoms, capturing them in a red magneto-optical trap intercombination line mod. It's still a bit too bright here to make a BEC, so we push them into a horizontal dipole guide where they fly through with like 8 centimeters per second, 4 centimeters away to arrive in a collection region. So there is a tiny little Siemens law down here, pushing the atoms into a reservoir. So yeah, okay. So we built this machine. It took mainly Shane and Shunshir. It took them like 4 years to build this vast setup. It's a bit of a monster because yeah, it was the first time we built something like this and we didn't quite know how to do it. So we over-engineered, made massive flux and implemented many different ways of making the transfer of the atoms from one stage to the other, but that blows up the size. Okay, if here is a Siemens law, often Siemens law 2D blue mod, and then the atoms fall down here. And if we zoom onto this lower region, here, you see the atoms in this artistic rendering falling down and being collected in this red mod. Okay, I told the graphics artist to make it blue. It just looks so much nicer. But it's a red mod down here. Then we push the atoms into the guide, Siemens law, and they are collected in this reservoir, where we also have the dimple and the transparency beam. And in reality, it looks like this. Okay, so this is the guide. Here's the Siemens law region. Here's the reservoir, and the dimple is barely visible, this little central part here. Now, we can't detect a BEC. Our imaging system doesn't have the right resolution, and it's just too dense too. So as usual, we switch all laser beams off, the traps off, and let the atoms fall and expand and obtain these images. Here you see the residue of the atoms from the guide, the Siemens law region, a reservoir and dimple, and nothing elliptical, no BEC. Let us perform a few experiments. So we just start our machine and load our reservoir, and then we suddenly switch everything off. After 1 second, yeah, we don't have many atoms in the reservoir. Let's load a little bit longer, and you see how the reservoir is filling up, and then suddenly, if you go beyond 3.4 seconds or so, we have a little elliptical feature in the middle. So, and you also see that after that, nothing changes anymore. So we have reached a steady state equilibrium. The atoms in the middle are so dense that there are like 100,000 of atoms per second lost by three-body recombination, but this is overcome by the continuous replenishing. So it's steady state. And here, this elliptical feature, that could be a BEC. Let's check. We just take an image before and after the appearance of this elliptical feature and fit it with appropriate thermal fits, Gaussians essentially. And the first image I can perfectly fit with such a thermal model. Whereas if I do the same thing for the second image, I do have a residue. Yeah? And that looks very much like I would expect from a BEC, also size-wise. Now, if I add a Thomas Fermi distribution to the fit, which describes a BEC, then I can describe both. We checked also in many other ways, like the moment that the BEC appears, the size of the BEC, atom number, it all makes sense. So this is a BEC, and it lasts in our machine for as long as we want. So the students try to, they dare to go to 5 minutes, and afterwards they were afraid the high power lasers would maybe burn the windows and stopped it. But anytime you interrupt randomly within 5 minutes, it's there. And the BEC is very small, by the way, it's 10,000 atoms only, and we are working on making this bigger. And so the new team is Junyu and Davide mainly, and they have the system. Now they want to, okay, make the BEC bigger, of course, but also add an outcoupling mechanism. And the outcoupling works in this way. We have the atoms here inside this gravity, yeah, potential. We have that inside the dipole trap. Now, strontium has also an excited metastable state, and if we choose colors of our dipole traps just in the right way, we can make it such that the trap just doesn't trap the metastable long-lived state. Now, this is, we need to transfer from the ground to the metastable state, essentially on the clock transition. To get strong enough, we implement a 3-photon transfer scheme, and then we hope that the atoms can triple out by gravity, just as they did in the old rubidium atom laser experiments. And Junyu already made this 3-photon transfer work, and here you see damped Rabi oscillations on the clock transition. Okay, now I asked Rodrigo to show you the lab. Let's see if the sound works.
Here is our atomic oven. Here we heat the strontium atoms to produce the hot vapor. The atoms travel through the Siemens lower axis, and then they are slowed down in our blue 2D mode. Now as we zoom in, the atoms are here, trapped and cooled, and they fall down to the bottom chamber. And it is in this bottom chamber where all the magic happens, and we've made the steady state VEC. Here in the closer shot, you can see some of the optics that we use, or transparency beam, and some of the mode optics. And some of the transport laser optics. So, thanks for coming. I hope you enjoyed this virtual lab tour, and I hope to see you again here soon.
Thank you, Rodrigo. So, okay, good. So I showed you how we created Bose-Einstein condensates continuously. And on the way towards this, we created this microkelvin called beam in the dark. And that's really also great to build optical clocks. So how do we do this? Okay, no, first, why do we want to do this? Now, overcoming the dig effect that I described to you already, but for clocks, there's even another, maybe more important reason, and that's the following. If you have a pulsed clock, each measurement gives you a precision of maybe 10 to the minus 16. But these clocks, they can go to 10 to the minus 18 or even better nowadays. And you reach this by brute force averaging, which scales with the one of the square root of the number of measurements. So to improve by this factor of 100, you need 10,000 measurements. Each measurement takes a second. So it's 3 hours of measurements for one data point of your clock. If you could measure continuously, you could phase lock your laser to the atoms continuously, and the next limit, if you do everything right, is a Fourier transform limit. And that scales with 1 over time. So to get a factor 100 better, you just wait for 100 seconds, 2 minutes. Think about how much faster the PhDs would be finished with their thesis. Right? So yeah, and also it's of course nice for any other application because it increases the measurement bandwidths of your clock. Good. So how do we reach this? Okay, we don't need, of course, a continuous source of atoms. Now, an atom laser is actually not needed. This microkelvin called beam here in the dark is just fine. And there are several different ways in which you can build continuously operating clocks. And one way that we are pursuing is to just feed this atomic beam into a cavity. And just before the atoms arrive in the cavity, you excite them to the upper clock state. And inside the cavity, you entice the atoms to emit their photon into the cavity mode, and out comes a laser beam on the clock transition directly. And it's not so super trivial to do this because the clock transition is very, very narrow. It's millihertz wide, so the lifetime in the excited state is 2 minutes. But you can exploit super radiance. Essentially, phase synchronizing your atoms inside the cavity. They do this automatically. And then the emission rate is massively enhanced and you can get this laser beam. Now, this is a laser, but it's certainly not a normal laser. So in a normal laser, the gain medium's line width is much, much larger than the cavity mode line width. And the frequency of the outcoming light is given by the frequency of the cavity mode. So it's the length of the cavity. This is a classical clock. And if vibrations or thermal noise change the length of the cavity, the phase of the outgoing laser beam will change. That's very bad. Now, in our case, the atomic transition is very narrow, and so it dominates. It defines the frequency of the outgoing light. And even if the cavity shakes a little bit and changes its length, the outgoing light's frequency is barely influenced by this. And this is why it's so nice to build a real clock out of it, a quantum clock. Now we pursued this along two paths. We have one machine in which it's a precursor Pathfinder machine, in which we use the 7 kilohertz line width transition as our pseudo clock transition. And to make a laser, a super radiant laser on this transition, we just have a strontium oven here. We send an atomic beam upwards. Then we have some stages in which we select just the atoms that barely move along the cavity axis to get rid of the Doppler effect. And we pump them first to the metastable state and then up here to the lasing state, the 3p1 state inside the cavity. And Camilla and Francesca, they can seed their cavity with a tiny little laser beam, and they see now here an amplification already by a factor of 4.4. So the system starts working. And Camilla then observed that when she just suddenly flashes on the final pumping stage to bring atoms from the metastable state into the 3p1 state, she sees a flash of light coming out. And that is very enticing. It lasers already on its own without any seed. It's just not yet continuous. And since then, a new team has taken over, and they're making good progress, I think. Good, and then we have a second machine, which is really working on the millihertz line width transition of the strontium, the millihertz line width strontium clock transition. And you see, it's a simplified version of our atom laser machine. Oven, Siemens slower 2D mod, red mod, and then a transfer into a science chamber where we actually have a ring cavity into which we load our atoms to create a super radiant laser. And Sean and Benedict and Ananya, they have pushed this to a red mod, and actually the performance of this machine, despite being 3 times smaller in each dimension, is the same as the humongous, gigantic atom laser machine. This is just because we learned so much what to do and how to do it that we could design it in a much more elegant way. And now this machine is taken over by the new team, Ying, and soon joined by yet another PhD. And then we hope we can bring the atoms into the science chamber and start working on atom cavity coupling. Then after starting this project, something peculiar happened. The Ministry of Economic Affairs gave us a lot of money to build the Dutch optical frequency reference. Now, if you want to provide a country with its frequency reference, you can't do it with an unexplored, completely crazy, fancy new type of clock. You have to do a little bit more, something more traditional. But then again, we wanted still to combine it with our continuous source technology. So Sumit and we had the idea of building a zero datum clock based on this continuous source. So here again, you see the same type of vacuum chamber, often Siemens lower blue mod, and then here the red mod. And in the red mod chamber, we have 4 black body shielded interrogation zones. And you can see, come on. You can see here, this is this continuous red mod. We have here a ring, cavity lattice, which is a conveyor belt that can bring the atoms from the center into above any one of these 4 interrogation zones, and then vertical conveyor belts with which we can bring them into these black body and magnetically field shielded interrogation zones. So we load one interrogation zone, and we will start Ramsey spectroscopy. Then while this spectroscopy is going on, we load the second zone. And then in a phase coherent way, we close the first Ramsey sequence with a pi over 2 piles and use the same pi over 2 piles to start the next Ramsey interrogation. In this way, if we phase coherently hand over the interrogation from one zone to the other. So yeah, we can phase coherently lock our laser to the atomic transition. And yeah, in this way, we hope to build a zero dead time clock. So, come on. Yeah, okay, and at the moment, okay. Yeah, so the machine has been baked, and Sumit and everyone are building the parts, that cavities and so on, that need to go inside this huge vacuum tank. Good. Okay, so this is our research on continuously operating clock. We also have a European consortium that I'm coordinating, in which we are building a transportable optical lattice clock with industry. So for example, here NKT and IXBlue and Wexlum and so on, they build these laser sources. Menlo Systems is a system integrator, combines it with a frequency comp. The French National Metrology Lab, they built the physics package together, supplemented by Torun. And in Amsterdam, we are building the optical circuits, the control electronics, and the low-level software. So if you were in an ultra-cold atom lab, you have certainly seen optical tables that look like this, crazy full with mirrors and lasers. And yeah, PhD students, they build this, and often it takes them months to build such a setup. And once it's done, you need to align all these little screws on the mirrors, and temperature fluctuations in your lab will misalign it. And after 2 weeks or so, you have to tweak many of these mirrors again. So it's a huge time effort. And if you want to sell a clock to a customer, can you rent your PhD student out to the customer? Not so much. So we went over and built a robot that is able to glue all such optics together in a nice way, in a very stable way. So it's a pick-and-place robot which just takes these optics pieces and puts them at the appropriate locations on this glass board, aligns the optics, and then glues them with UV curing glue. And we have built 6 such circuit boards, the ones that are needed to build an optical lattice clock, and put them in a vibration isolated manner into drawers, integrated them into the rack here at Menlo Systems. That was done last August, and the boards work since then very nicely. And they also, look very, oops, oh no. They also look very pretty. Okay, so this was most of what we are doing in the direction of quantum sensing. We have also a few activities in the direction of quantum simulation, rubidium-strontium molecules and virtual coupled strontium atoms and tweezers. Just briefly what we do here. So on the rubidium-strontium project, the last thing we did was we measured the nuclear magnetic moment of strontium-87 very precisely by using rubidium as a co-magnetometer. And we are interested in studying strongly interacting mixtures, and rubidium-87 and then fermionic strontium-87 together, they happen to have a humongous interspecies scattering length of 1,600 Bohr. And usually in 3 dimensions, that means your gas burns away in no time by 3-body recombination. But we found that if we confine the gas in 2 dimensions with a 1D lattice, the loss gets just nearly completely suppressed, and we have a long-lived system. And that's very great. We then used this and the confinement-induced resonance to create rubidium-strontium molecules. At least we think we did. And now, good, then the machine completely broke, but it's back on track, and we are trying to spectroscopically prove that we really did so. And this research was so important, apparently, that even Emmanuel Macron from France, the French president, has to come over to congratulate the PhD student, Bram Thekpat. And he brought the buddy, his king, along. Okay, and on the tweezer experiment, one of the last things we did was the following. So in tweezers, you always want to rearrange your atoms. Typically, you load only every other tweezer with one atom, and you need to look where you have atoms and then resort them. And that can be done with acousto-optic deflectors, but it can also be done with spatial light modulators. So spatial light modulators, you just put a hologram on them, and that creates then these patterns that you see here. And nowadays you can purchase spatial light modulators with an update rate of a kilohertz or so. Now, to move these atoms around, you just start at some position and then you hop your laser beam from image to a new position. Now, the challenge we found is the following. The SLM, if it switches from one pattern to another pattern, the tweezer, it will display both images at the same time in between. And if the two tweezers, the initial one and then the final destination one, have the same phase, the intensity of light just smoothly moves over as you desire. But if there is, by chance, a pi phase shift between the two tweezers, they interfere destructively in the middle and it blinks out and the atom is lost. It's really terrible. And the standard algorithm to calculate these holograms, the Gershberg-Saxon algorithm, uses these phases for other things. So you don't really have a control over what you get as phases. And so we adapted it and made it such that the neighboring phases of moving tweezers are always close to each other. And in that way, we could smoothly move atoms from one position to the other, very competitive with the ALD sorting schemes, even for thousands of tweezers. And we also did this now in 3 dimensions. Good, and last year, we had a lot of fun with Christiane Moraes-Smith theory group. She is an expert on fractals, and yeah, she loves interacting fractals. So we put our atoms on this teeny tiny Sierpinski triangle. It's first generation fractal, and studied the transverse field Ising model and looked at how the spins flip if you scan through these different phases. Okay, so this is all I wanted to tell you. And of course, to do all this research, you need great people, and here are the real heroes of the story. Thank you very much.
Thank you, Florian. So we started late by about 6 minutes, so there's a little bit of time for questions. I can't see the audience, so I don't know how this is managed. Pankaj, can you help, please?
Yeah, very impressive body of work. So I had a question regarding your continuous loading.
Yes.
Sorry, excuse me. So you have the dimple trap, which is operational, and now you have this way of detuning the atoms in the dimple while you are implementing the loading. The question I have is that, I mean, why does the dimple trap, the atoms which are preloaded at any given time t, survive the loading? Because all atoms which are in that volume will get affected the same way. So how does the process actually work? How do you manage to continuously load without an equivalent loss?
Okay, so the atoms come into the reservoir trap, and there you do have laser cooling. So there's at least naively no problem there. And then I think you were concerned about the transparency beam of the dimple, right? So this transparency beam only influences the optically excited state of the laser cooling transition and very quickly shifts this to 10 megahertz. And the transition is 7 kilohertz. So this is very quickly a massive shift. The region of danger, maybe, where you could think the laser cooling beams become resonant with the atomic transition, is so minusculous that it doesn't really matter. So the atoms randomly are scattered into the dimple. They are decoupled from the laser cooling process, but you still have plenty of elastic collisions. So there's nothing dangerous happening in the dimple region. But there is something dangerous actually happening in the outside, in the reservoir region, because there, the dipole trap we are using right now, it makes a differential light shift on our laser cooling transition. And right now it's a little bit badly chosen, and actually the frequency of light that we need to laser cool the central part of the system is fluidly tuned towards the free space atoms in the outside part. And there actually, exactly, I think what you were fearing happens. And we actually lose currently 90% of our atoms. So we send 1 million atoms per second into the reservoir, but only 100,000 per second arrive in the dimple. And we want to overcome this now by choosing a different wavelength for our reservoir dipole trap. And in our simulations, that shows we can overcome this loss. And that would, yeah, hopefully massively increase our loading rate. Then we can get more stable and bigger BECs.
Thanks.
I can't see the audience, so I don't know what questions there may be.
Any other question?
Yeah.
So for the BEC laser, I mean, so what fixes the frequency and the wavelength of how do you control that?
You mean the atom laser itself?
Yeah, the atom laser.
Okay, so it's phase evolution and such, right? Okay, so the BEC has a phase, and if everything was nice and no fluctuations, then that phase would be just transferred to the outcoupled atom laser beam. However, in our system, the BEC is coupled to the thermal reservoir. So there are constantly atoms leaving the BEC, becoming thermal, or the other way around. So the number of atoms in the BEC fluctuates a lot. There's a lot of change then in the mean field, and that changes the phase evolution of the BEC, and thereby then the phase evolution of the atom laser beam. So I think this laser, if we ever manage to make it, it will be very phase noisy. So there you would have to use other techniques. And we are thinking about this. So for example, yeah, you would need a big puddle of a big BEC. So there I'm thinking of implementing an evaporative cooling stage where the atoms drift down a guide, evaporate sideways, and then they arrive at a huge accumulation region where you can have a humongous BEC that hopefully is a little bit more phase stable, and then outcouple from there.
Florian, maybe I ask a question. Can you hear me?
Yes, we hear you, yes.
Okay. So a bottleneck in these tweezer arrays for quantum simulators, of course, is continuous loading. They're making headways into it now. Can you combine your two methods to make it work?
Yeah, I mean, people have done this, not really continuously, but in a kind of a pulsed manner.
Yeah,
there are
in the
several
pulse,
groups
but,
who have done this. No? Michel Lukin's group has done it. In Munich, there's an experiment having done it.
Yeah.
Maybe even more nowadays.
They're just beginning to do it, yes.
Yeah.
But the actual commercial machines are not pulsed.
Yeah, that's really where you want to go, and it's relatively easy to implement. Yeah.
Hmm. Good. If there, again, I cannot see the audience. I know the camera is not.
Yeah, there is one question here.
But if there are no more, are there questions? Or?
Hossein, there is one question from a student.
So,
Sorry?
in the atom laser, so if I want to just crudely understand it, what is the characteristics of the atoms which are coming out in the atom?
The statistics.
Yeah, I mean, you are you form a BEC and then you outcouple the atoms. So in a simple way, is it the distribution of the atoms, like the way, if I correlate it to the lasers, the photons there is a coherence. So in that way, what is the characteristic of
the atom number statistics? What's special about it? So this was studied with pulsed atom lasers, for example, by Tillmann Esslinger a long time ago. So you look at, for example, the G2 function, just like you would for a normal optical laser, and you see that instead of thermally having this peak at a short time of 2, it flattens out to 1. Maybe that answers your question.
That will be the case even in the atom lasers.
Yeah. That was studied with bosons, with fermions, with fermions, you get a suppression.
Okay, then if there are no more questions, join me in thanking Florian for a beautiful talk.